So our final part 3 of topic 26, discovering properties of exponents, we're going to look into zero powers as well as negative powers. So here, what happens when you raise a number to the 0th power? Look for a pattern as you fill in the table below, then evaluate each expression using what you know about dividing a number by itself. So here, we have 2 to the 4th divided by 2 to the 4th. Now we know from part 2 that when we divide and we have the same base, we're really subtracting. So every single time here, when we reduce our 2 divided by 2, 2 divided by 2, 2 divided by 2, 2 divided by 2, we end up simplifying to 1 times 1 times 1 times 1, which when you multiply them all together, that product is 1. So 2 to the 0th power is 1. Now we can do the same thing with 5 to the 6th divided by 5 to the 6th. So here, if we were to subtract them, we would get 5 to the 6th minus 6, which would be 5 to the 0. And if we expand it, like they did in the example right above, we get 5 times 5 times 5 times 5 times 5 times 5 over 5 times 5 times 5 times 5 times 5 times 5. And we can reduce. So here, 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 and here. And when we reduce, again, that just equals 5 to the 0th power, or 1 times 1 times 1 times 1 times 1 times 1, which just reduces to 1. This applies also to negative numbers. So we have negative 8 times negative 8 times negative 8 over negative 8 times negative 8 times negative 8. If we want to reduce, that reduces to negative 8 to the 0th power, which also reduces to just 1. And again, same with 9 squared. We have 9 times 9 over 9 times 9. And if we want to multiply this one out just to show another way, 9 squared, or 9 times 9, is 81. 9 times 9 is also 81. 81 divided by 81 is 1. So this is really 9 to the 0th power, which reduces just to 1. So as we've seen from all of these 4 examples, any time that we raise a number to the 0th power, we end up getting 1. But there's this special case here with 0 to the 0th power. Now this is a little bit tricky because you'd assume, oh, 0 is a number, so if we raise it to the 0th power, we should get 1, right? Actually, this is undefined. Because we have conflicting patterns. So if we do an example that we did before, let's say we have 0 to the 5th power divided by 0 to the 5th power. Now, if we were to solve this by subtracting, we get 0 to the 5 minus 5, which would get us 0 to the 0th power. But if we were to expand this, we have 0 times 0 times 0 times 0 times 0, all over 0 times 0 times 0 times 0 times 0. Now here, they all cancel out, but can we actually divide by 0? Ooh. No, we can't. We cannot divide by 0. If we divide by 0, that's undefined. Think back to slope dude. If you divide by 0, it's undefined. However, there are some other interesting cases. So what if, for example, we have 0 to the third divided by 0 to the first? Well, if we subtract that, we would get 0 to the 3 minus 1, which would be 0 squared, and 0 squared, that's 0. So here we're dividing by 0, but when we subtract, we end up getting a positive exponent. What if we have 0 to the third over 0, oops, let's see if I can, no, whoa. Sorry, a little bit there. Let's say this is 0 to the fifth. So here, if we subtract, we get 0 to the 3 minus 5, which is 0 to the negative 2. Now, we'll learn in a few seconds that when we deal with negative exponents, we're actually going to move them to the denominator. And here, this is undefined, because we cannot divide by 0. So we have conflicting patterns here. Sometimes when we subtract and divide by 0, if we end up with a positive exponent, we get 0. But if once we subtract and we have a negative exponent, and we end up getting, once we subtract and we end up getting a negative exponent, then it is undefined. So this, unfortunately, does not work. There is no specific rule, it's just undefined here. If we move on to the next example, we had a little sneak peek of negative powers. So what happens when you raise a number to the negative power? We're going to look here. So in the example here, they had 2 to the second over 2 to the fifth. So they expanded it just like we would see, but we're actually left with this 2 and these 2 2's. And they are in the denominator. So notice how when we subtract, we have 2 to the 2 minus 5, and we get 2 to the negative 3. Well, where are our 2's located? They're located in the denominator. So our answer is also going to be located in the denominator. So that's the same thing as when we have a negative exponent. It can become positive if we transfer it to the denominator and bring its base down with it. Now just its base here. So let's expand this. We'll have 4 to the fourth, which is 4 times 4 times 4 times 4. Over 4 times 4 times 4 times 4, times 4 times 4 times 4 times 4 times 4 times 4. And if we want to reduce, we have here, 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 and here. And we're left with these 6 4's. So here we have 4 to the 4 minus 10, which is 4 to the negative 6, or the same thing as 1 over 4 to the positive 6. We can do the same thing with negative numbers here. So we have negative 9 times negative 9 over negative 9 times 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 negative 9. And we can reduce. So we end up with our 5 negative 9's in the denominator. We can prove that with negative 9 to the 2 minus 7, which is negative 9 to the negative fifth. Or if we want to write that with a positive exponent, which we always write as a positive exponent, that is the proper way to write this. So that's the same thing as 1 over negative 9 to the fifth. Now we can do the same thing with exponents here. So we have a to the sixth, b to the fifth. So we have a times a times a times a times a times a times b times b times b times b times b, all over, oh goodness, a times 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 a over b times 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 b, ooh, squishing in there, and we can reduce. So our a's reduce here, and we're left with these 3 a's right here, and our b's reduce. And we're left with all of our b's down here. So if we subtract, we're left with a to the negative third times b to the negative seventh. And if we want to write that as an exponent, we would have, with positive exponents, we'd have 1 over a to the positive 3 and b to the positive 7. Now, if one of these exponents right here, if one of these exponents happened to already be positive, we would not need to move it. It would stay in the numerator. However, here, since we are dealing with both negative exponents, we need to move each base separately. But since they're multiplied together, that's why we can write them in the same fraction. So the pattern that we see here, and this is a little lengthy, we need to subtract the exponents because we're dividing. And if the exponent difference is negative, we are going to rewrite as a fraction. With the positive exponent in the denominator. So if we were to write a general rule for this, whenever we have a negative exponent, like we have our negative n right here, we're going to write that as 1 over x to the positive n. And this works the other way too. So if we have a negative exponent in our denominator, we can move that to the numerator to become positive. So here, we would end up getting 7 to the positive 3 over 1, or just 7 to the positive 3. And there you have it. That is part 3 of topic 26, discovering properties of exponents.